All right, ladies and gentlemen, this is the penultimate presentation, lecture, whatever you want to call it, module number 8. We're almost there. Number 9 is an extra. I will not quiz you, and you will not have... there is a quiz, but I'm going to give you full credit for the quiz. If you want to take it, take it. If not, you're okay. And I'm not going to include anything from module number 9 in the final exam, so it's an extra. So this basically is the last one, but then I'll record the next one and put that out for you guys. So, tools for assessing an association. Remember how we said that like there's an association between coffee and pancreatic cancer, but it's not a causative association. That's that. And so we've looked at methods for numerical outcomes, right? Categorical predictor, 2-sample t-test, and ANOVA. Remember, ANOVA is for when we're comparing the means of 3 groups. Group 1 is equal to the mean of group 2, which is equal to the mean of group 3. The t-test is more for comparing the means of 2 groups. X2. Numerical outcome with a numerical or categorical predictor, simple linear regression, and then numerical outcome with several predictors, multiple linear regression. Right? Y, the expected Y is the intercept, plus B1, X1, plus B2, X2, all the way to the last B. Plus an error term, but we assume that the error term is negative, is 0. So we will cover the methods for categorical outcomes. Categorical outcomes with a categorical predictor. Chi-square. This is chi-square. It's written chi-square. Don't make the mistake that I made and call it chi. That's T, which is delicious. Binary outcome with a numerical or categorical predictor. Uses simple logistic regression. Binary outcome with several predictors. Uses multiple logistic regression. Okay. So binomial proportions. Binomial, yes, no, 1, 0, up, down. Advanced melanoma is an aggressive form of skin cancer that until recently was almost uniformly fatal. Research is being conducted on therapies that might trigger an immune response to the cancer. A study where 52 patients were treated concurrently with two new therapies, and 21 had an immune response. So you kind of start looking at this immune response. So yes, no, right? Did you have an immune response? Yes or no? And you have two categorical, right? You either got Nimulev or this other one, and they're not ordinal, they're just nominal, right? One doesn't come before the other. Questions that can be addressed with inference. What is the estimated population probability of immune response? Following concurrent therapy with one of the two drugs. What is the 95% confidence interval for the estimated population probability? Again, probability of immune response. Probability of yes, given something else, right? Where the probability of or the proportion of an outcome given that you know what the exposure is. All right. In previous studies, the proportion of patients responding to one of these agents was 30% or less. So these results suggest that the probability of the response to concurrent therapy is better than 30%. So we kind of start making some assumptions here on what the two hypotheses are going to be, right? Melanoma data are binomial data, with success defined as experiencing immune response. So we can code it as 1 equals immune response. And 0 as no immune response. Suppose X is a binomial random variable with parameters n and p, where n is the number of trials, p is the probability of success. So then the inference is made up of the population parameter, p. The probability of success in the population. The estimate for p from the observed sample is p hat. Okay, where x is the observed number of successes. So how many people did have an immune response over the total number of people? That is their p hat. And then we can estimate that to the population. It can be made using the normal approximation to the binomial or directly using the binomial distribution. Why? Because the n is large enough that we can use a normal approximation. Hopefully this is bringing back some memories from the earlier chapters. The sampling distribution of p hat is approximately normal when the sample observations are independent and at least 10 successes and 10 failures are experienced in the sample. So n times p is greater than or equal to 10. And n minus 1 minus p, failures, is greater than or equal to 10. Remember, we need to have these to hint for your final exam. Under these conditions, p hat is approximately normally distributed with mean p and standard deviation. This is your standard deviation. Since p is unknown, but the population is unknown, it is necessary to substitute either p hat or p0 for p when using the standard error of p hat to compute confidence intervals and conduct hypothesis testings. In the context of calculating confidence intervals, substitute p hat for p, and so the two-sided 95% confidence interval for p is given by this. And remember 1.96, the z critical value for 95% is 1.96. 1.96. That should really stick with you guys, right? And you do this you can do this in R, and it'll do it for you. In the context of a hypothesis testing, substitute P0 for P, and you get the Z, and then you ask yourself, whatever Z I got, is it within negative 1.96 and positive 1.96, or is it outside? And if it's outside, reject the null. But if it's inside, fail to reject the null. And what did we get here? 95% confidence interval. So we're saying that we are 95% confident that in the population, the response is either between 0.29 or 100%. Okay, but the alternative here is greater. Right, so pay attention to those little details. Remember, our alternative is that P is greater than 30%. An exact inference for binomial data, P binom. Okay. Lower tail equals false because, again, it's greater. Or use the binomial test. The exact binomial test. Probability of successes is this. So this is our estimate of successes in the population based on this sample. Because we got 21 successes, and this is our trial, and our p-value is this. So our p is greater than 0.05. So we're going to have to do what? Fail to reject. Why? Because the confidence interval here includes 0.30. Right? So if we're saying, is it bigger than 0.30, but the confidence interval includes it, then it's not going to be significant. Difference in two proportions, kind of the same as the difference in two means, right? Except that, the two samples are independent and at least 10 successes and failures. So you can, the same as the other one, hint again for the final. The standard error of the difference of the sample, this big old formula, just know where to plug in your numbers. The proportion in group 1, the successes in group 1, failures, successes, failures. 1 minus p, we usually call it q. So you might see me sometimes write pq for that. That's just an old-fashioned way of doing it. In hypothesis testing, the following estimate is used to compute the standard error. So this is how you do that. Okay. So for an example, here, a 30-year study to investigate the effectiveness of mammograms versus a standard non-mammogram breast cancer exam in Canada. Here's your N, pretty big. That's why we can use the approximation to the normal. By the end of the 25-year follow-up period, 1,005 women died from breast cancer. The results are here. Right? Proportion test. Test of two proportions. Two sample tests for the equality. So here our null is that proportion of 1 is equal to the proportion of 2. Our alternative is that the proportions are not equal. Okay? Number that 500 mammogram group who died, control group who didn't. Our n's, our totals, right? Chi-squared is right there, 1 degree of freedom. And this degree of freedom is not equal to n minus 1 like the other ones. This degree of freedom is the, when you do a 2 by 2 table, is the number of columns minus 1. Multiplied by the number of rows minus 1. So this is 1 and 1 is 1. P-value, way big. This is a chi-square distribution, so I'm not going to draw a normal distribution. It's really skewed. But it's basically saying that the probability of a type 1 error is very high here. So fail to reject your null, please. And you see it, if your null is that the difference is that they're the same proportion, then your difference is 0. And so your confidence interval includes 0. And then the two-way tables. Two-way table summarizes information about the relationship between two categorical values. Testing for a difference between P1 and P2 is equivalent to testing for an association in a two-way table. If you remember this, positive predictive value, negative predictive values, right? So we're going to look at single dose nevirapine is given to an HIV positive woman during birth to prevent mother-to-child transmission of the virus. Cuba, by the way, doesn't have any more mother-to-child transmission of HIV. They've been very good at getting every woman tested for HIV and then giving them antiretroviral therapy. Exposure of the infant to NPV may foster the growth of resistant strains of the virus. If the child is HIV positive, should he or she be treated, or a more expensive drug? So 2 by 2 tables, we usually set them up, and you saw this when I was doing the positive predictive value, negative predictive value, and I call them A, B, C, and D. Just keep that in mind. So here A is 60, B, C, and D. All right. So children were randomized to either this group or this group. And when you do good randomization, these two numbers should be just about the same, and they are. Virologic failure or stable disease, 87 and 200. So the question here is virologic failure related to any of these drugs? Or is stable disease related to any of these? Do the data support the claim for a difference in the outcome by treatment? So is this outcome different depending on what treatment you get? Is 60 and 27 different than 87 and 13? Your null hypothesis treatment and outcome are not associated. Your alternative is that they are associated. It is always inherently a two-sided alternative. Hint for your final. Chi-square test of independence. This is we do the chi-square test. Pearson chi-square test, not chi-square. Chi-square, chi, C-H-I, square. And when you write this, it's kind of hard. A lot of people like to write an X, but it's not an X really. It's kind of this weird X-looking letter. Anyways, the test statistic quantifies how far the observed results deviate from what is expected. So what is expected, right? Again, we're talking in this observed minus expected over the expected, or over some sort of standard error, right? So what is expected? Well, it's expected that if everything is the same, then all A, B, and C, and D would be the same, right? But they're obviously not, and so how far away from not being the same are they? Are we seeing some sort of variation here just by chance, or is it really something in there? So expected cell counts. If treatment had no effect on the outcome, what would we expect to see? Ooh, remember this? Right? So we would expect to see the probability of A and B equals the probability of A times the probability of B. Expected cell count in the upper left corner A would be 44.56. right? If everything was equal. Okay, look at this again. You had 87, and this is how it splits out. So then you would say that multiply these down here, and that's how you get your expected. All right, just take a look again. Understand what you're filling out. So the expected count for the ith row and j column, row total times column total divided by n, which is the number of observations. Row total, column total divided by n. Your row total times your column total divided by n. Independence. Each case that contributes a count to the table must be independent of all cases in the table. Hint, again, in linear regression, we talked about LINE or LEIN from the book. Sample size. Each expected cell count must be greater than or equal to 10. Be careful with low sample sizes. It really screws with your statistics. For tables larger than 2 by 2, it is appropriate to use a test if no more than 1/5 of the expected cell counts are less than 5. So this is something that we use in epidemiology a lot. If we have anything less than 5, we don't even analyze it because it's just going to be biased. Your chi-square statistic, look, observed, expected, overexpected. And because this difference of here might be negative, we square it. Degrees of freedom, I already told you, R minus 1, C minus 1. Rows and columns. And we let R do all the work. So we put in the table A, B, C, D, 60, 27, 87, and 113, right? 60, 27, 87, and 113. So know how to construct the table and know how to plug it in. Hint. How many rows, how many columns? So we're telling R what these numbers, how we're going to put them in. By row equals true, right? So this is a row, and then this is the next row, right? The name says this is just to create the table with its proper names, and then we do a chi-square on that table. P-value less than 0.05. Reject the null and go with the alternative. So what is, in terms of the null, there is no association. The alternative, there is an association. The null, the observed minus the expected over the expected squared is equal to 1. The alternative is that it is not equal to 1. Right? It's just saying that what we observed is what we expected. And adding it all up. So here you have your table based on the statistics here. Again, the p-value. And then we also do the residuals because we want to make sure the magnitude of the effect. If a residual is positive, the observed value is greater than the expected value. If it's negative, the observed value is less. So yeah, it's how this is working out to be. Hint for your final exam. The residuals, you do the chi-square test, p-value, and then you do the residuals, and here they are. Don't worry too much about this, just know what they mean. And measures of association in 2 by 2 tables. Relative risks, this is what we use in epidemiology a lot. Okay, this is the risk in one group, and this is the risk in the other, so the relative risk is 2.11 So the children treated with NPV are estimated to be more than twice as likely to experience virologic failure. Right? So how many experience virologic failure over here? What proportion? 40.8%. What proportion here? 19.3%. Right? So the NPV group had higher risk of virologic failure than the LPV group. Relative risk. We can also use odds. Odds ratio is a measure. So the odds of NPV, of virologic failure in NPV, the odds is 0.69 or 69%. And the odds is 0.239. Again, the odds is bigger in the NPV group than the LPV group. You might be confused at times between risk and odds. They're two different things. All right, probability and odds. And so just one is using odds, the other one is using probability. And odds is taking us towards logistic regression. But again, that's all extra. Just know the difference between an odds ratio and the difference between a relative risk. The relative risk cannot be used in studies that use outcome-dependent sampling, such as a case control study, when we begin the study by knowing whether you were a case, you were sick, or you were a control, you were not sick. Then we need to use odds ratios. But if we begin with healthy people and we give some people one drug and other people another drug and then look at the outcomes, then we can use relative risk. Even when it is not possible to estimate the incidence of an outcome, odds ratio is still valid. And for a very rare disease, very rare, where prevalence is less than 10% or so, odds ratio approximates relative risk. All right. So that's it. If you have any questions, comments, concerns, you know how to get a hold of me. We're almost done. One more lecture. Number 9 is extra. Just go ahead and take a look. I will quiz you, and you can answer the quiz if you want. You can leave it alone if you don't want to do it. You'll get full credit for it either way. Okay? Thank you, and have a great rest of your day.